Let's jump right in. Welcome to this explainer. Today we are focusing exclusively on section 6.4, comparisons across frequency and across time. We usually just think about hearing in terms of volume, right? Like how loud or how quiet something is. But the reality of how our auditory system actually processes the world is so much more complex than that. To really understand how we make sense of sound, we have to look past the raw data and dive right into the incredibly sophisticated comparisons our brains are running constantly in the background. To kick things off, let's ask a really fundamental question. How do you actually know an E is an E, whether someone is whispering it across a dead silent room or shouting it over the noise of a busy street? Your brain just instantly recognizes that specific vowel sound, totally regardless of the volume. So how is that even possible? What exactly is your ear measuring to get that kind of consistency?
Well, to answer that, we're going to follow this roadmap. We'll start with absolute versus relative intensity. Then we'll move into a really cool process called profile analysis, and finally, we'll wrap up with comparisons across time.
Okay, let's jump straight into section 6.4.1, absolute and relative intensity.
The really crucial distinction we need to make here is the difference between what a sound is and where it is. Absolute intensity, which is basically the raw sound pressure level, is definitely useful. It tells you how close a sound source is. It's essentially your proximity alarm. Think of a siren coming down the street. That absolute intensity warns you it's getting closer. But when it comes to identifying what that sound actually is, absolute intensity is surprisingly useless. Instead, your auditory system relies entirely on relative intensity. It is constantly calculating the exact ratios and the differences in volume between all the different frequencies that make up a single complex sound.
And this beautifully illustrates that exact point. If we take an E vowel spoken softly at, say, 50 decibels and compare it to that exact same E spoken loudly at 100 decibels, the overall energy, the total height of the wave, shifts completely. But look at the relative peaks and dips. The fundamental shape of the wave stays exactly the same. Your brain actually ignores that massive shift in overall height and just locks onto the shape. That spectral shape is essentially an auditory fingerprint. Because your ear is calculating the ratios across those frequencies, rather than just measuring the raw volume, your brain flawlessly identifies the exact same vowel, whether it's a whisper or a shout.
Moving right along to section 6.4.2, profile analysis. We call this incredibly precise process profile analysis. Basically, this is your ear mapping out the holistic shape, or what we call the spectral envelope, of a sound across its entire frequency spectrum. It's not just isolating one pitch, it's simultaneously comparing the levels of a bunch of different pitches all at once, taking in the whole landscape of the sound to recognize its unique contour. Researchers actually wanted to prove exactly how much we rely on this relative mapping. So David Green and his colleagues set up this brilliantly simple spot the difference game for the ear. They synthesized a complex spectrum made up of multiple pure tones playing at the exact same time. Now, in one interval, all the tones were completely flat, perfectly equal in intensity. But in the other interval, one specific tone, the target tone, got an incredibly slight volume bump. The listener's only job was to figure out which interval contained that microscopic bump.
But to make absolutely sure listeners were using profile analysis, the researchers introduced a real stroke of methodological genius. You see, if they had kept the baseline volume the same every single time, a listener could just cheat, right? They might just listen for whichever interval sounded louder overall. So to stop that, Green completely randomized the overall loudness on every single trial. One trial might be booming, the next might be barely audible. Absolute volume was completely wiped out as a reliable clue. Listeners had no choice but to ignore the total loudness and exclusively scan for that relative internal shape.
And you know what? The results definitively proved our auditory system is custom-built for this. Listeners can naturally and easily detect tiny decibel changes between frequencies. They successfully found that target bump even while the overall volume was jumping wildly up and down. And this specific ability to isolate relative features is absolutely critical. It is exactly how we pinpoint the defining frequency peaks of human speech. Without this innate ability to map those relative shapes, completely ignoring the overall volume, we just wouldn't be able to pick out specific words in a noisy, dynamic environment. And what's even more fascinating is how this mechanism ties directly into our memory. If I asked you to remember the exact, absolute, raw volume of a single tone, your memory for it would actually fade remarkably fast. It drops off into pure guessing in just a few short seconds. But our memory for a sound's relative shape, it is incredibly robust. Green's research showed that listeners could perfectly recall a relative spectral shape, that unique acoustic envelope, even with extensive delays of up to 8 seconds between the sounds.
So why is there such a massive difference in retention? Well, it's because it's so much easier for our brains to store simple structural categories. Instead of trying to maintain this massive, constantly updating spreadsheet of exact decibel data points, our brain basically acts as a master of biological data compression. It simply categorizes the profile structurally. It just says, okay, this is bumped or this is flat. All right, let's wrap this up with section 6.4.3, comparisons across time.
So we've established how we analyze the profile of a sound in a static moment, right? But time is the final essential ingredient here. Think about this amazing contrast between our senses. A perfectly still, static visual image, like a printed newspaper page, gives you a massive amount of complex, dense data. You can sit and read it for hours, extracting new information. But a perfectly still, continuous, unchanging sound, it gives you almost zero information. As the source material dryly notes, I can say E for as long as I like, but you wouldn't learn very much from it. Except, well, maybe about the state of the speaker's mental health.
True auditory information relies entirely on variability. To go from a meaningless static hum to conveying critical, life-saving information like the phrase, evacuate the building, the sound waves have to change. Specifically, to identify complex signals like speech consonants, think of the hard, sharp onset of a P or a T sound, we absolutely rely on rapid, dynamic micro-explosions of acoustic change. It's the drops and spikes of sound intensity over time that actually carry the meaning.
To study this, researchers measure our dynamic tracking through a process called increment detection. Instead of giving you two separate sounds with a big clean pause between them, like we saw in static profile analysis, increment detection tests your real-time processing. It measures how well you can hear a tiny, sudden intensity bump placed right inside an ongoing continuous sound wave. It literally tests your brain's ability to track fluctuations in real time without taking a single break.
And the results of these experiments are pretty mind-blowing. They show that our temporal resolution is razor-sharp. Our auditory system isn't just sensitive to static shapes, it is incredibly sensitive to extremely brief, fleeting fluctuations. We can accurately compare intensities over incredibly short time intervals, seamlessly tracking millisecond by millisecond changes. This high-speed temporal tracking is the final key mechanism that actually allows us to perceive fluid human speech.
So we've seen that our ears largely discard raw absolute data. Instead, they're tuned almost exclusively to finding the differences, the structural contrasts in frequency, and those rapid millisecond by millisecond fluctuations over time. And it leaves me with this thought. If our entire auditory reality relies so heavily on relative comparisons rather than absolute levels, what other parts of our world are we only truly understanding through contrast and change? It's definitely a fascinating way to look at how our nervous system interprets reality. Thanks so much for joining me for this explainer.